Welcome to the presentation on the geochemistry of the Jarosite-bearing shale layer in Matanomadh, Kachchh. This work is part of a dissertation conducted under the guidance of Dr. Alik Majumdar, Assistant Professor, Department of Applied Geology, Indian Institute of Technology, Indian School of Mines, Dhanbad, Jharkhand. This study focuses on the geochemical characterization of carbonaceous shale samples collected from the Matanomadh area in Kachchh. The aim is to analyze the elemental composition of the shale and determine how these elements influence the formation and geochemistry of the jarosite mineral found within the Matanomadh formation. There were various tests and analyses that were conducted throughout the dissertation period. To arrive at a conclusion, the workflow included three objectives. 1. Studying the samples of carbonaceous shale obtained from various locations at Matanomadh, where the outcrop of Matanomadh formation has been exposed. 2. To use the powdered sample for X-ray diffraction test and inductively coupled plasma optical emission spectroscopy. This is the most crucial step as it includes sample preparation, which governs the whole geochemical analysis to be done further. Third, using the results obtained to know about the elements contributing to the anomalous occurrence of jarosite. Geochemistry can be simply defined as the use of chemistry and its various theories and tools to solve geological problems. The geochemical data includes information on distribution, abundance, and composition of chemical elements and isotopes present in geological materials. Such an information helps understand the genesis of a particular rock, the geological setting of its formation, and the various possible processes which have occurred and are active in an area. Results from two conducted tests contribute important insights into the core argument of the dissertation. These include powder X-ray diffraction and inductively coupled plasma optical emission spectroscopy. The powder XRD is an analytical technique that helps identify the various mineral phases present in the sample through diffractograms obtained on testing. On the other hand, ICP-OES enables rapid multi-element analysis of the digested samples. The samples used for the above tests is carbonaceous shale, which are rich in organic matter and widely recognized as significant petroleum source rocks worldwide. These shales are typically dark, laminated, and enriched with organic material and iron oxides, commonly in the form of pyrite. Geochemical analysis done on shales provide insights into sediment provenance, paleoclimate, tectonic setting, basin evolution, and fluid rock interactions, including small-scale hydrothermal processes. Such data help develop analogies and theories of geological processes. The Kachchh Basin is an east-west extending pericratonic rift basin that lies in the state of Gujarat, western India. It developed as a result of successive rifting and tectonic movements associated with the northward drift of the Indian plate following the late Triassic to early Jurassic period, during the breakup of Gondwana. The Nagar Parkar Fault in the north, Radhanpur-Badmer Arch in the east, and the North Kathiawar Fault in the south border the basin. Figures A and B show the location of the Kachchh Basin and the major faults that bound the Kachchh Basin. The basin experienced significant tectonic events during the Cenozoic, which greatly influenced its geological evolution. It contains a complete stratigraphic sequence from the Triassic to the present, attracting considerable interest from geologists due to the diverse geological structures retained within it. Moreover, the basin has been regarded Category 2 type sedimentary basin having contingent resources with pending commercial production. The basin experienced drifting nearly 70 million years ago, which developed horst and graben structure followed by Deccan volcanism. The main study area of research is the Matanomadh present in the Kachchh Rift Basin. It is located nearly 86 kilometers northwest from Bhuj in Gujarat. Figure 2 shows the location of Matanomadh to the northwest of Bhuj, marked with a black box. The Matanomadh formation of Paleocene is exposed as semicircular outcrops at the study area, bordered by tertiary deposits. The Matanomadh formation lies on the Deccan Traps and consists of a lower laterite member and upper clastic layer. The clastic layer hosts carbonaceous shales. On close analysis, jarosite was seen to appear in pockets and lenses within the carbonaceous shales. Jarosite is a hydrous sulfate mineral which forms an acidic and hydrous environment and is also reported from the planet Mars. Also, the occurrence of jarosite at Matanomadh along with its phyllosilicates is very much analogous to the geological environment of jarosite hosting localities on the planet Mars. Hence this analogy has raised inquisitiveness among the researchers to probe into its formation at Matanomadh. The methodology of the dissertation includes two important geochemical tests: X-ray diffraction and inductively coupled plasma optical emission spectroscopy. Before starting with the tests, sample preparation is the most crucial step. 11 samples were finely grinded and powdered using an agate mortar and pestle. Contamination was checked out by cleaning the agate mortar before and after using it for powdering. Bulk rock X-ray diffraction. X-ray diffraction is based on Bragg's law given by English physicists Sir W. H. Bragg and his son Sir W. L. Bragg in 1913, which describes the conditions under which X-rays or other electromagnetic waves are diffracted by a crystal lattice. It states that constructive interference occurs when the path difference between waves reflected from successive crystal planes is equal to an integer multiple of the wavelength. The law is expressed by the equation n lambda equals to 2d sine theta, where n is an integer representing the order of diffraction, 1, 2, 3, etc., usually taken as 1. Lambda is the wavelength of the X-ray beam. D is the spacing between the crystal planes, also known as the D spacing, and theta is the angle between the incident X-ray beam and the crystal planes. Figure 4 shows a schematic representation on the working principles of XRD. Clay separation XRD. Clay separation was performed on 4 samples. The peaks obtained from bulk rock XRD did not confirm the clay minerals and several peaks remained unidentified. Therefore, clay separation using a centrifuge machine was done to separate the smaller particles from coarser ones. The method is based on Stokes' law. The supernatant on centrifugation contained the smaller particles, which are 2 to 0.35 micrometers small. The prepared sample was sent for X-ray diffraction. ICP-OES. It is an analytical technique used to measure the concentration of elements which range from a few parts per billion to hundreds of parts per million. The quantity of light emitted by an atom at each wavelength and the position of the photons is calculated by the instrument. This gives the type of major, minor and trace elements and also approximates their concentration. The reagents used were hydrofluoric acid, nitric acid and hydrochloric acid. JB1B, basalt, obtained from the Geological Survey of Japan, was used as a standard in the test. 100 mg of the 11 powdered samples, a duplicate, a blank and the standard were measured using the weight balance machine and put into the PTFE vials, along with 3 ml of milliQ water, followed by 3 ml of hydrofluoric acid, 3 ml of nitric acid, and lastly, 1 ml of hydrochloric acid were added to the above sample in the PTFE vials. This is regarded as triple acid digestion. The procedure was followed by close and then open sample digestion. The samples after open digestion yields a precipitate which is sealed in a volumetric flask with 1 normal nitric acid and is sent for analysis. Powdered carbonaceous shale samples of size approximately 64 micrometers were analyzed using X-ray diffractogram with a copper K-alpha radiation source at 2 theta angles. The 2 theta angle range taken was 5 degrees to 80 degrees. The result obtained shows a stacked diffractogram in figure 7 with some prominent peaks that correspond to particular mineral phases, mostly illite, kaolinite, and quartz. Clay separation XRD was performed when it was observed that some peaks still remain unidentified after bulk rock XRD. On performing clay separation on the 4 powdered samples and analyzing the separated sediment particles of nearly 2 to 0.35 micrometers size, it is found that illite is the major clay mineral present in the samples, with some minor montmorillonite. The stacked diffractogram in Figure 8 shows the XRD peaks after clay separation. Figure 9 is a comparison figure which shows stacked diffractogram of bulk rock XRD peak and clay separation XRD of 4 samples SMK by 2A, SMK by 2, SMK 3 by 3, and SHK by 4. 4 minerals are identified overall: illite, kaolinite, quartz, and montmorillonite. Major, minor, and trace element data were obtained for 11 samples, a duplicate, blank, and the standard JB1B basalt from the ICP-OES examination. From this data, values of aluminum oxide, calcium oxide, sodium oxide, and potassium oxide were normalized and plotted on a C&K triangular plot which shows weathering trend. The direction of the red arrow from plagioclase towards kaolinite and illite explains their abundance in the shale sample. It can be suggested that the large amount of kaolinite and illite is a chemical weathering product of plagioclase present in basalts of the Deccan Trap. Also, values plot more on the aluminum oxide side, which is an important oxide component in kaolinite and illite. This confirms our findings from previous tests of XRD and ICP-OES. The geochemical tests identified major peaks which correspond to illite, kaolinite, and quartz. On separating clay fraction from coarser particles and performing XRD, the dominancy of clay mineral illite was again observed in the sample, with very low amount of montmorillonite. ICP-OES data on calculations shows aluminum oxide, potassium oxide, sodium oxide, ferric oxide, and titanium oxide values to be in considerable amounts, with very low amounts of manganese oxide, phosphorus pentoxide, calcium oxide and magnesium oxide, indicating more aluminum present in the samples as compared to iron. This again aligns with the fact that illite is the dominant clay mineral observed in the sample. Also, less iron predicts no clue for specific iron oxide minerals, which is characteristic of carbonaceous shales. The AC&K plot also shows that shales contain a very small amount of sodium in them, and the majority of samples plot on the illite kaolinite side of the triangular plot. The study conducted on carbonaceous samples leads to the following conclusions. 1. The carbonaceous shale sampled from Matanomadh on analysis gives aluminum, potassium, sodium, and iron, which contribute to the chemistry of jarosite. These elements come from the chemistry of minerals like illite, kaolinite, and from the lower stratigraphic rocks such as laterites and basalts. It can be said that illite, kaolinite, and montmorillonite have originated from the chemical alteration of the lateritic layer of the Matanomadh formation. 2. The presence of an iron sulfide mineral which is characteristic of carbonaceous shales is still unidentified. None of the peaks exactly correlate with any iron oxide mineral diffractograms. 3. Large amounts of the clay mineral illite in carbonaceous shales indicate conversion of kaolinite to illite upon diagenesis. Kaolinite starts to convert to illite when temperatures reach around 100 to 150 degrees Celsius, though this can vary depending on other factors such as the availability of potassium in the surrounding environment, burial depth, and fluid interactions. I hope this discussion on the dissertation titled Geochemistry of Jarosite-bearing shale layer in Matanomadh, Kachchh helped you understand the overview of the studies conducted. The year-long work comprises sample preparation, geochemical analysis, and working with the obtained data from analysis to look into the issue. It can be concluded the elements potassium, aluminum, sodium, and silicon have been leached out of the laterites, which are also a weathering product of basalts. Thus, the chemistry of jarosite can be a result of geochemical interactions, fluid rock interaction, and diagenetic processes occurring in the area. Once again, I hope the work displayed in the presentation would have given valuable insight.